piece of candy, a bottle of liquor, I mean, sorry, whatever you wanted to buy. Okay. We're gonna introduce two terms today, but before we introduce those two terms, we wanna look at a review of internal forces, okay? Now, earlier when we were doing trusses and supports, okay, we mentioned that when we were working with those, we do not include two force members, because at those ends of that member, those forces are opposite to one another. They cancel each other out. But we do need to put those into account when we're looking at shear or bending. Okay, so if I've got a two force member, and I'm gonna put point A and point B. If I'm doing this at point A and this at point B, this is a tensile pair of forces, or a tensile couple. Okay? Just a reminder, if you've got it the opposite, we've got A and B, and we are here with our forces, we have a compressive pair of forces for a couple. Okay? Now you're probably thinking, why is that important? Why is that important? Well, with the section we're going to look at, with the shear, with the bending, those forces become important. Remember, in trusses, those were lightweight, rigid components that did not perturb, did not change. Well, now we're going to look at how things change.
Yeah, if something changes in a truss, it's normally...
It's a detrimental change, right? It breaks, okay? And when it breaks, it shears. Okay, so that's where we are. So before we had our sum of our forces and our moments equal to 0, because nothing's gonna move. Here we're gonna set our forces and our moments to a max value to see when they move. Okay, because they're gonna move. Okay, we can't build anything like that. Okay, so in everything we do, we need to make sure that we can draw that free body diagram. You got a free body diagram, that's gonna be the most important thing you learn in here, is how to draw it, okay? And guess what, when you move into dynamics, if you have to take dynamics, what's the most important thing you're gonna do in there? Draw a free body diagram, okay? So we're stationary here in dynamics, it's gonna begin to move. So we've got different types of beams that we're gonna look at. So let's say we have this beam here. This supported here and here. Now it could be supported at a pin connection. Could be supported at a roller connection if it's one designed to expand and contract. This is called a static beam. Okay, this is called a static beam. It doesn't change. Okay, if we have a beam that looks like this, where we have a support here, and a support, I didn't mean to call that an A, and a support here, this is called an indeterminate static beam. What's the difference between the two?
Unbalanced supports?
Unbalanced supports. So what does that mean about the forces?
Not balanced.
Not necessarily not balanced, they're gonna be unequally distributed. Okay, so if we put a weight here on a static beam, okay, if we put a weight here, what can we look at it in terms of?
Whole beam.
Well, the moment with respect to point A and point B, right? If point A is here, that would be the weight times that distance, right? Would have an effect there, which would have to be counteracted by what? The forces at A and B pushing up, okay? So you see where I'm coming from? With this, if I was to put a force there, my forces still have to be counterbalanced by what's at A, B, and C, since I've got 3 supports. But I can't necessarily just straight plug into my moment equation, because what happens? I now have something in between. Or if I use this point, I've got something on that side and something on this side. So we're gonna have a little bit different free body diagram for this. Okay? I have this type of beam here. This is called an overhanging beam. What is an overhanging beam? It's got something hanging out there. It's kind of like the drive. To me, it's very reminiscent of a gas station that has just one set of pumps. You've got the roof that comes over and extends over that set of pumps. An old-timey gas station. Okay, not one that's got its own freestanding roof. Just the roof comes over and the beam hangs over. You don't want to support out here. Why not? Because you want to drive out there, right? Okay, so now we've got this kind of support. Okay, it's mounted here, probably in a wall. Okay, this is called a cantilever. Beam, okay? All of the forces are incident back here, right? Now, sometimes a cantilever beam may have a different shape other than just a uniform shape. It may look like, we're looking at the cross section, something like this here, okay? Why?
Support's easier.
It's not that it supports easier, it distributes the forces closer to the support out here. If we just have a uniform beam, what's going to happen to those forces? They're going to be distributed somewhere out here. If we've got it in this shape, they're going to be distributed closer back to the mount. Okay, that's what we're looking at. Okay, so we have also a beam that's semi-fixed or fixed in support. Okay, so we have a fixed in support. Okay, if you ever think about, I don't know if you know much about barn construction or pole barn construction, but if you have a pole barn and you have a drop shed, you know, an open part of the shed that's off to the side, that's a fixed in support beam system. Okay, because what have you got here? You've got some kind of header out here at this point where your beam's set, but they are connected to the main structure up here. Okay, they're just resting out here. Probably in our area, they're resting with a hurricane strap on them so the hurricane don't make them flop. Okay, and then we have a complete fixed support between two structures. Okay, so we have a complete fixed beam. In each of these cases of beams, what happens? The free body diagram changes because of the distribution of the forces that are associated. Okay? Now, with that, each type of beam can experience something called shear or bending. Okay? What is shear?
Cross force.
Okay, it's a, well, maybe not a cross force. Bending would be a twist or an arc, okay? But what would shear be?
Separation.
Separation at some point of our beam. Why is it separating? Because the forces are greater that's exerted on that point than what the beam can withstand, okay? So we're gonna be looking at those shear forces and that bending, okay? So we're gonna be looking at shear forces and bending. So in doing that, we've got to make a few definitions. start off with shear. Okay, let's start off with shear. Shear is positive when the shear force does what?
Pushes.
Causes it to break. Causes it to break. Bending is positive when we have a parabolic shape that looks like this. So when we put some external forces on there, shear is caused by external forces as well, not the internal forces. Remember, what are the two internal forces we have? We have tensile force and we have compressive force. Are they gonna cause it to shear?
They're gonna try to hold it together.
They're gonna hold it together or they're gonna cause it to explode. Okay, which is not shear. We're looking shear as just a, and I'm gonna say this loosely, a uniform tear. A uniform tear, not an explosion, okay? So for instance, if you have a concrete beam, very evident in concrete beams, how are concrete beams produced? There are wires in there or rebar in there that are stretched. They're stretched. The concrete is poured and hardens, and then the tension is left off of the rebar to do what? To push the concrete together. And when it does that, what does it do? It tends to make a slight arc, okay? Compresses the concrete. But if you press that concrete more, what's gonna happen? It's not gonna just shear, it's going to explode. Suppose you put that concrete on a road structure and support both ends and not take into account the coefficient of linear expansion, and it gets really hot. What happens? It bends. Okay, same thing happens with a railroad track, except the railroad track doesn't go up, it goes
sideways and knocks the train over.
Okay, so bending is positive when we have that. Shear is positive when we have a breakage. Okay, so if we've got a beam that looks like this, I'm going to put point A at this end and point B at this end, and somewhere in the middle I have point C. Not in the exact middle, but somewhere in the middle I have point C. Okay, so if I put a force here, and I'm going to say this is 10 pounds, and I put a force here, which is 20 pounds, can I describe what's happening to that beam? Now, this is a very, very thin beam if it's going to experience shear and bending, right? It's going to be very, very thin or very, very limber, okay? So, how can I describe this? How can I describe this? I can describe it in terms of a free body diagram, right? A, C, B. What are my forces? If I support my beam here and here, what are my forces?
Your normal force or your...
Okay, I've got a reactive force here, right? To the weight of the beam plus the weights that are on there. I've got a reactive force here. What else do I have? I have a 10 pound here, and I have a 20 pound here. Now, could I find any information from that? Yes, I could determine the reactive force at A and the reactive force at B. How can I do that? The sum of the moments at A are equal to what?
0.
0. and the sum of the moments at B are equal to 0. Now you notice here, they're not equally dispersed. They're not equally dispersed. So I would have to know this distance or this distance or this distance to solve for one, then solve for the other. Okay, and you're thinking, duh, that makes total sense. It's nothing different than what we've been doing. There is nothing different than what we've been doing, unless this force set of forces causes this. Let's see. Unless it causes that. Okay, when that is the case, I have a moment here in this direction. Okay, and I have a shear force here in this direction. Since I have those, I have another moment in this direction, which I'm going to call moment prime, and a shear force in this direction, which I'm going to call B prime. And you're looking at that, oh, I don't agree with that. I don't agree with that. But remember our definitions. What were our definitions? For V to be positive, it's got to do what? Cause
Break.
a break. Would this V and this V prime be equal? Or would this M and this M prime be equal?
Yes? I don't know.
Think about that. When would they be equal?
When the break.
When the distances are the same and the incident forces are the same. The incident forces are not the same. Have you ever, I'm not going to do it because I'll get in trouble, okay? Have you ever seen the science trick where they take a piece of newspaper and lay it out on a table and put a meter stick under it and hit the meter stick and the meter stick breaks? Have you ever seen that? Think about that. There's more to that trick than just the air resistance of the newspaper. It's how far the meter stick sticks out. If the meter stick sticks out really far, so that I've got a long lever, and I hit it, what happens? It brings up the whole piece of newspaper. If I slide the meter stick back, so that I've only got a small lever, and I hit it, what happens to the meter stick?
Snaps.
The meter stick snaps. Okay? The same principle is at work here. Distance is important. We know that because what is moment? What is a moment? It's a force acting through some perpendicular distance. So we're not introducing anything new. Okay? We're not introducing anything new. We're just applying it. Now, with beams, I'm showing you here that we have uniform forces at one location. We could have a beam. I'm a really bad straight line drawer. Yeah, it just goes downhill every time I try to do it. I bet I could do it if I didn't have lines up here. Okay? We could have a force like that exerted over a distance. Now we're in simple stage. We're going to assume what? That that's a uniform force if we've got a straight beam. But what if we have a beam that looks like this? What if we're designing some new casino alcove and it looks like that. Like a wave. We're gonna paint it blue and put a little bit of white froth up at the top, you know, to make it look like it's a wave. And now what if we have
Unequal forces.
what are we gonna have to do? What's the difference between this one and this one? Y'all are taking math and you know the difference. Here we've just got a straightforward equation, right? Here we're gonna take what?
Integral.
An integral of the what?
Curve.
Curve. From point to point. That's all we're gonna do. That's all that's different about chapter 7 than what we did in chapter 6. There's no other difference. There's no other difference. There might be a total of 8 pages of stuff in your book on chapter 7 other than examples. Okay? So, that's it for what we're gonna do today as far as chapter 7 goes. I've got 4 problems picked out to work in class on Wednesday. Now, I know that you have homework due Wednesday, right?